Okay, good afternoon all. Today we shall see what Unix files are and what different files exist on Unix platform. So there are different kinds of files as you can see here. There are regular files where you can store user data. Then directory files. They basically allow you to store the file names and also the inodes. We shall see what these inodes are. Then symbolic links. If I want to give another name to the same file, so it can be through a symbolic link. Yes, somebody is requesting join.
No, sir, I guess Pooja is waiting.
Yeah. So you have regular files, you have directories and symbolic links, and there are hard links also. We shall see the difference between hard link and symbolic link. Then we have device files, like we have character device files and block device files. So character device file, a good example for this would be your keyboard. So keyboard being a device, that will also be treated as a file. Similarly, the hard disk. So hard disk will also be treated as a file, and it is block disk because it will allow you to transfer data in chunks, whereas character devices allow you to transfer data one character at a time. Then we have already seen FIFO, the IPC mechanisms. One of the IPC was FIFO. That was called as named pipe. That is also categorized as a file. And sockets, which we shall be looking at these things subsequently. So as you can see, there is a wide range of different files, and how to deal with them is what we shall see in this session. Now, what is interesting to note is that even the devices are treated like regular files. Okay, so whenever you open a file, if it is a regular file, you get a file descriptor, and if it's a device file, you get a device file descriptor, and through that you can communicate with the device. So that is how the things are kept so simple. Now, to maintain the information about the files that you create, there is one structure called as inode. So inode is a kernel data structure which maintains metadata, that is the data about the file. For example, you can know what is the file size, then who is the owner of that file, what permissions that file has. So whenever you create a file, you being the owner, you can give permissions to others or people in the group. So what permissions exist? When you create a file, you have all the three permissions: read, write, execute. Uh, if you have set those settings, and for others, you can give permissions as you wish. Similarly, at what time the file was created, what was the file type. So when I say file type, it can be one of these 7-8 types of files. So there are different symbols to indicate different types of file. For example, you want to see a regular file, and when you do ls-l, you will see first letter as dash. Okay, and if it is a hard link, you will see an L there, and if it's a directory, you will see D. Okay, so to indicate data of different types. Similarly, if it is a block device file, you will see B. If it's a character device file, you will see C. So the first letter when you give ls-l tells you what type of file it is, whether it's a directory file, regular file, a link, or a block file, or a character device file. Similarly, you can see when data gets stored on the disk, so there are pointers pointing to the data blocks on the disk. So there are pointers associated with the file, and those are all stored in the inode. And it also maintains one count called as hard link count. Hard link being a pointer to the same file, you should know how many references are there to that file. So whenever you want to delete a file, you must see that the hard link count has gone to 0. So until such time, you cannot delete the file. So that is the reason hard link count is maintained as part of the inode structure. Similarly, the file will have other attributes. The file permissions, when I said read, write, execute, it is for users, groups, and others. So there will be 9 characters, 3 for each. Okay, so whenever you do ls-l, you will see read, write, execute, then just read, write, dash, then read, dash, dash, something like this. So what it means is these characters refer to the owner. It means the owner has all the three permissions: read, write, execute. These three characters refer to the group. So here group has only read, write permission, no execute permission. And then others who don't belong to the group, they have only read permission. So this is how you have to interpret. So all that is stored in the file attributes. So there is one more structure which will maintain this. Similarly, the ownership of the file, who is the owner of the file, the user ID and the group ID will be stored. Along with this, there are few other things like sticky bits, set UID and set GID. We shall see all these things subsequently. Then there is a umask also, determines default permission bits when file are created. So default permission bits means when you being the owner, when you create a file, you will have all the three permissions. Now, what are the different system calls that are used when you want to create files, you want to read files, and you want to do all the necessary IOs? So these are the different file input output system calls. So you should be aware of these, and we'll see how to use them. So open is a system call which is either used to open an existing file or create a non-existing file. So create is also there, but it is not advisable. It is not again POSIX standard. So you use open with certain argument which will allow you to open existing file, also create a file. So we shall see how to do this. Then once you open a file, then you can perform the read write operations. And finally, you must close the file so that the data structure associated with the file are all released to the system. Okay. Then once you open a file, if you want to navigate through the file, you want to go to a particular line number or number of bytes away from the beginning of the file, then you can use lseek. And the attributes which I listed above, that is who is the owner of the file, what file permission, what is size of the file. If you want to find all that, there is a stat or fstat API. Okay, so this is used to retrieve the metadata. Okay, so these are the different file APIs that will be using, and some of the tools that you normally use at the shell prompt. The ls command allows you to see the file permissions, the type of file and all that. Stat is again a shell command which will allow you to find out all the file attributes, and there is a file command to know the further file details. Okay. Then lsof allows you to list open files across processes. So many processes would be running, and all files which are opened by different processes can be listed using this. Okay, then we have strace and ltrace. We shall see all these subsequently. Okay, now what is important to know that whenever you create a file, there is a very complex data structure which is maintained within the system. So there is a file descriptor table which is within the process. Then there is a file table and a inode table. These two are in the kernel space. So if you look at this diagram, things will be more clear. So whenever you open a file, there a process will maintain file tables, and these file tables are nothing but an array of pointers. Okay, and index into this array of pointers is your file descriptor fd. It's an integer value. Okay, so remember this file descriptor. So every process will have this table. As you can see, process 1 has its own file table, process 2 has its own file table like this. But in the kernel space, there is one common file table. Okay, so this is a system level file table where the file mode is stored in what mode the file is opened, whether read mode, write mode, read write mode, and then access permissions of the file. Okay, and then the offset, the current offset where the file pointer is pointing to. Okay, and this file table contains reference to the inode. Okay, so there is a inode table also, as you can see here. So inode table again has a very complicated structure here, and one of the member will be pointing to the data blocks. We shall see in great detail the structure of the inode that is maintained here, and this is where the actual data blocks are. Remember, if you have a file called hello.txt, let us say some 100 KB, maybe 20 KB stored here, 20 KB here, 20 KB here, like this. 5 data blocks are required, 4 5. Okay, so all these data blocks belong to file hello.txt, and there will be pointers pointing to this. So there will be direct pointers like this, and there will be indirect pointers also. We shall see what those indirect pointers are. There are about 12 direct pointers. If number of blocks are less than 12, then this table only contains the pointers to all the blocks, and you can read these blocks and make it available to the process. Okay. Now you all might be wondering why such a complicated kernel structure is required. That is because same file may be used by more than one process. For example, file 1 is opened by process 1, and process 2, if it opens the same file, so then will be a reference here, and the reference count here will be 2 now for the same file. Okay, so you don't create one more inode structure here for each process. So there will be only one inode structure even though 2 processes have opened the same file. It is not that 2 processes are required to open the same file. The same process may open the file twice. Okay, so that is also possible. In that case also there will be a reference counting, that is through the hard link that I discussed earlier. Okay, so as you can see here, the file descriptors in the process have pointers to point to the file table, and file table has permission read, write and all that, and this is the inode table where the file is actually stored on the disk blocks. So the diagram here is more provides more clarity. So pay attention and look at what this diagram is. So this is the process table where the file descriptor provides an index into this array, and this points to the file that is open with whatever permission. So as you can see, this file is opened with the read write permission and pointer to the inode here. And inode is not just one entry there, it contains all these things. So it will tell you in what mode you have opened the file. Okay, then what is the hard link count here, who is the user of this table, or owner of this table, in which group that owner is there, what is the file size, at what time the file was created. After all this, you have address of first 12 disk blocks. So if file size is small, then these pointers only point directly to the disk blocks. There are 12 of them, 1 to 12. But what if the file size is more than 12 disk blocks? In that case, there will be indirect pointers. So what this single indirect pointer point does is it will point to another table which contains pointers to the disk blocks. Okay, so this is a single redirect. Then even these are exhausted. Let us say there are again 12 of them. So 12 plus 12, 24 pointers we have, or 24 blocks. Suppose the file is of 30 blocks. So then again you require double indirect. So this will point to another block which contains an inode. This inode points to another block, and this actually contains the actual pointers to the disk blocks. Okay, so multi-level hierarchy exists. So triple indirect is also possible. So this pointing to this pointing to this, and again this pointing to this. And these are the actual pointers pointing to the disk blocks on the disk. Okay, so this is a complicated structure which is maintained by the kernel, and as and when you open files, close files, all these updates will be happening. And if whenever you open a file and perform read and write, it will check whether you have the required permissions or not, looking at this entries here in the file table. And also whenever you do a read, it will take the file offset and start reading from there. Okay, and if you perform a write operation, the file size will be updated. And if you open a link to the existing file, the link count will increase. And if you whenever change the mode of the file, the mode will get altered. Okay, so all this will be happening as and when you open a file and perform read write operations. Okay, is the structure of the inode and this is clear to you? Hello?
Yes, sir.
Okay.
Yes, sir.
No doubt, right? Okay, now let's see how to use these things, how to create files. But only thing is, at the back of your mind you should know all this is happening in the background. It doesn't show up when you perform the programming on the Linux platform. So, and it is important to close the file, because if you don't close the file, all these pointers and all these entries in the file table and inode table will be open, and they eat up the system resources. Okay, so one thing is you must open the file to perform read write, but once you are done with read write, you must close the file. Okay, so that you must remember. Okay. So let's see how to use all the system calls and perform some basic operations. So let me first show you very simple one. Now suppose if I want to open a file in read mode, so all that I have to do is I should declare an integer variable fd, and then fd equal to open, and you must give the file name here. Let us say test.txt and o read only. I want to perform only read here because it's an existing file. Okay, and you can check whether this file opening was successful or not by putting a if condition. So if first assign it to fd and check if it is less than 0. If it is less than 0, then you are unable to open the file. The reason could be the file may not exist, or you do not have permission to open that file in read mode, anything. So you can do a p error and you can just give open. It will automatically append what is the reason why you are not able to open the file. That is the advantage of using p error. And then you can do a return 1 here because the opening was not successful. When you come out of this if, it means the file is opened. Now you want to read the file. So for reading the file, you require some placeholder, because data is going to come from the disk blocks on the disk. So we don't know how big the file is, so we can define some character array here, call it as buffer, and provide some 1000 bytes. Okay, and here you have to do a read operation. So while read fd comma buffer comma size of buffer, and this read will continue to give you value greater than 0 as long as there are enough data is to be read. So while this is true, you perform the read operation, and when you perform a read, it may not read all 1024 bytes, it may read less than that. So actual number of bytes read, you can keep a count of that. You can say int bytes read. bytes equal to, so that as and when you read those many bytes, you want to write that onto the screen. So as long as there are enough bytes to be read, you can, after reading, you can write this onto the screen. Std out file number comma buffer comma bytes read. So what this does is it will keep reading the bytes from the opened file until all the data in the file is read, and then here you can close the file. For closing the file, just you don't require the file name, you just require the fd. Okay, so this is the process. Okay. Now let's see whether it works fine for us. gcc file1.c. So now there is a test.txt. Test.txt. It contains this text: hello, this is this and Unix system programming session. So let's see whether it prints that. The file name is in test.txt. Okay, test.cx. Okay. As you can see, it opened that file, read the entire file and displayed it on the screen. Is this clear? How to open a file and read it? Or any doubt here?
I mean, got a bit of it, sir. Maybe if we try, we'll get it.
Yeah, you have to practice this. I will share the code with you, and then you have to do this on your own and get acquainted with all the syntax of it. Okay. Now we know how to open an existing file, but what if I have to create a file? Okay, so let's see a file of that type. So that is nano file create one.c. create one.c. Okay, now let's say I want to create a file and I want to write this message into that file. Let's see whether that happens. So for creating a file, again you have to declare a file descriptor, and this time you can have one variable number of bytes written. Okay, so you can open a file first. Here, open. Name of the file, let us say I want unix.txt or something, anything. You can give any name. So this file should get created. Okay, and then you have to specify certain flags here. O create. Then you are writing to the file, so O read write. Or if you want to only write, O write only. Okay, and then one more flag, O truncate. Now what this O truncate does, if the file contains something already, it will delete that and then write this new message onto it. Okay, so, and then the last one is with what permissions you want to open that file. I want only read write permissions for all, so 066 is what you have to provide. Okay, so this file, if it does not exist, it will be created, and once that file is created, you can write to that file using write API message, and then size of, and you can note how many bytes were written. So bytes return, of course, whatever you have specified, those many bytes will be returned to the file, and then here close FD. I'm a little doubtful about this, but anyway, let me check if it works fine for us. VCC file create 1.c minus o. Okay, there is a spelling mistake here. I have to execute this. Yes, we have this unix.txt created here, and if I do a cat, you see that same message which I wrote has come here. Hello, this is Unix system programming. Okay, so this is how you can create a file and perform write operation. Okay, so you should once you practice, you will always remember these things: o underscore create, o underscore write only, o underscore truncate. If you have if you want to open the same file for read write, you can do r rd wr. Okay, so read write both will be there. So after writing, you want to perform a read and display the content, you can do that. So that is about opening the file for write purpose. So I have an example for read write also, for write read. So let me check that also. File write read.c. So here, as you can see, I am opening a file in both read write mode, rd and wr, and again o truncate. But this time I am opening a file which is sent as a command line argument. If you remember, in C programming, we had int argc and char star argv. Do you remember this? These are called command line arguments, and it will be an array of strings stored in this pointer. Okay, so what I do is, what I expect is, whenever I run this program, after the file name, I should be providing the file which I want to open for write and again perform a read on it. For example, name of this file is file write read, and after this I should say test.c or whatever. So that file will be opened for read write, and once the file execution is correct, then you can perform a write operation on it, as we did, message and its size, and close the FD. So after writing, I am closing and again opening the file here, the same file, for read only. So read operation we know how to do. Once you get the file descriptor, you have to perform a read with the file descriptor, buffer and its size. Keep reading this in a loop until you are done with reading all the characters in the file. So number of bytes read will be returned each time you perform a read, and same thing you can write it onto the console. Okay, so we know this file, we know this unix.txt exists. So first let me compile this file write read.c minus o file write read. Now the way to use it is fwr and then provide a file name here. If you don't, then it will tell you usage. It means it is unable to run because it expects a file name after the executable. So here you must provide the file name unix.txt unix.txt. So now it will open the existing file, and then you can see this is a test message returned to the file. Okay, so earlier content is overwritten because we have seen o create o truncate. So the what we wrote to unix.txt is overwritten with the new message that is there in the file, and that is what is returned to the file, and it is read and completed. Okay, so these are basic read write operations. Okay. All right, now coming to we have all these files. I told you that we can provide a link to an existing file. Suppose if I say ln-s unix.txt. So here -s means it will provide a soft link. Okay. So now if I say ls-l, you will see where is it? What was the command I gave? unix.cxe. Okay, I did not provide the link here, so I should have given, let us say, un.txt. Now if I do ls-l, you will see that un.txt is pointing to the same file. Okay, and then if I say un.txt, it will display the content of the original file. So this is not a file on the hard disk, it is only a pointer to an existing file name. Soft link means that. Okay, so I'll show you the distinction between soft link and hard link, which will be clear here. So if you have a soft link, it will point to the original file. Okay, and this original file will point to the disk blocks. Do you understand this? This is the difference. So soft link points to the original file, whereas hard link, it doesn't point to the original file name, it will point to the disk blocks here. It means it will point to the inode structure, and from there it knows how to access the data blocks. So if I create a hard link, then let us see what happens. Now the way to create hard link is just say ln, then unix.txt. You can call it as hun hard link, whatever. And now if I do ls-l, this hun.txt, it doesn't show a pointer here, but if you traverse back and see, the hard link count is incremented by 1, so the count has become 2. Similarly, for the file, Unix original file, the hard link count is 2. Okay. If you try to delete unix.txt, it doesn't allow you to delete that because there is a, see, it shows an error. You have tried to delete a file and the link exists. Okay, so the deletion actually is illegal, and you will see the hard link count is reduced by 1, so the file still exists. Okay, you have to remove this hard link, and then the file can be deleted. So remove hun.txt, can do ls-l. The hard link count is now 1. Now you can remove unix.txt, and now everything is gone. So the file unix.txt is gone. You don't see that file anywhere. Okay. So there is a distinction between soft link and a hard link. Now, is it only through the command line we can create soft link and hard link? No. You can create soft link and hard link through a C program also. Okay, so for that let us see a small program. Symlink.c. So here, if I want to create a symbolic link for a file, let us say there is a file char style original file equal to test.txt. So this file, we know it exists, and then there is a link file is equal to, let us say, new link. You can give any file name, doesn't matter. Now if I want to create a symbolic link, I just have to say symlink original file, comma, link file, and you can check whether this is successful or not and report. That is, if this returns 0, you can say printf soft link created, else printf soft link failed. Okay. So this is a way to create a symbolic link. So then you have to do a gcc symlink.c -o sl. I think so one extra bracket is required. And this is become extra. Expected comma. Okay, so I missed a comma here. Again I missed the comma. So now if I run SL, soft link created. Now if I do ls -l, you will see the new link txt is pointing to test.txt. Okay, so if I say cat test.txt, it contains this, and if I again do cat new link.txt, it should display the same because it refers to the same file. Okay, so this is how I can create a symbolic link. And if you wanted hard link, then there is a API. I think so. It is not symbolic. If you just use link instead of symlink, it will create a hard link. Just that you have to give a different name. And if I compile this again, of course the message should have been hard link created, but if I do ls -l, you will see h new link is created here and the count is incremented by 1. This is hard link count or no? Okay, now as you can see, test.txt is pointed by new link, and this, so the hard link count is incremented by 1 more. So here it is 1. So test.txt is pointed by this, also by this, and that is why the count has become 3. Okay. So when you create a file, its link will be 1. Whenever you add a soft link, it is incremented by 1, and when you do add a hard link, it is incremented by 1 more. Okay. So this is how we can create files of different types. Now how do I display the file attributes? So there is a file, there is a stat function, we shall see that. Now suppose if I am to display the file, whether it is a regular file or directory file or is a link or whatever. First thing is you declare a file pointer, file name of the file in a variable, and define a structure called as stat. So struct stat is defined in sys/stat.h. Okay. So this contains all the file attributes. So you just have to say stat file name. You don't have to open the file. In all my earlier example, I was opening the file. You don't open the file. You just mention the name of the file in the stat API. And second argument should be address of this structure. So this address, this variable structure or this structure file stat will be filled with all the data pertaining to the file, namely what type of file is it. Okay, so there is a member variable called as stmode. So stmode contains what type of file it is, and to instead of you checking individual bits of this variable, there are some macros available. For example, s_is reg. So this will return true if the file is regular file. If it is a directory file, then it will return true if I call the macro s_is dir. Then I want to check whether it is link or not. s_is link. So likewise you can know what type of file it is. So test.txt is a regular file, and if I run this program, it should show me it as a regular file. Similarly, if I want to know its size, it is displaying currently. To know the file size, all that I have to do is fstat.st_size. So there is a member variable called as st_size that will store the file size. So directly you can know how many byte it occupies on the disk. Okay. Now, if I want to check whether it is a link file, then I can check it using the different file name. So let me check which are the links we have. So for example, new link is a link file. So let me pass new link.txt to this. New link.txt. So this time I should compile it again. As you can, okay, the message has to be changed here. This, why is it printing regular file? Should this should be h new link. Should display link file. New link is a link file. So as you can see, the first letter is L. So it should display it as a link file or link hello.txt. It should be. Why it is not printing link hello.txt? Let's see. Still it is displaying regular file only. I think so. There is some bug in this program. I will check that. Okay, so using this stat system call, you can find out the statistics about the file. There is a stat command also. If I say test.txt, this will display everything. As you can see, this is a file of size 96 bytes. It occupies 8 blocks on the disk. Okay, and it is a regular file, and it has an inode number 11313. As I was telling you, every file is associated with a inode, and if I only want to know the inode number, then ls minus I, then test.txt if I write, then I get the inode number corresponding to that file. So this inode number refers to the inode corresponding to that file, and if you open up this particular block, it will contain all the statistics about the file. Who is the owner of the file, what is the size of the file, what are the read write permissions, and all that. Okay, so stat will help you find out all the details of the file. For example, here the read write permissions of the owner, group, and others. Who is the owner of the file, that is the user ID is this, and group to which he belongs to. Okay, so group ID is 1000, it corresponds to same user ID, and when was it last accessed, last modified, and last changed, and when it was created. So all these statistical data you can find out using the stat shell command. Okay, so same stat API also allows you to extract all this information from the inode structure. Remember, all this data is coming from the inode structure in the kernel here. Okay, so file size which is displaying, it is coming from here, user ID is coming from here, GID is coming from here, link count is coming here, the time which I showed you, access time, modified time, the creation of time, the file when it was first created, all that will be stored here, and the inode number corresponds to this entire block. Okay. Right. So you need to go through a few of these programs and try to create files, modify files, okay, and then try to create symbolic links or hard links and see whether what is happening to the hard link count which is displayed here. So few read write operations you must perform. Okay, so is the concept about Unix file is clear? What all types of files we can create and how to perform read and write?
Yes.
Okay, so I'll share the code with you. You go through this today and see if you find any difficulty, we shall see in our next session. All right?
Okay.
Okay, we'll close for today then.
Thank